Okay, we study C22, Newton's universal gravity explains Kepler's laws. This text can be found by visiting kpop.org. That is our library, Kpop library. And if you find the table of contents, you have Escape from Scientific Absurdity C series. This is C22. So click here and scroll down to find C22. You can find the textbook here. And if you click this, you can watch the same video in Korean. And now it's an English version. Okay. So C22. Please remember it's working. If you click this, you will find the Korean version of the lecture. And this is English version of the lecture. And you can click this to go back to our K-pop library at kpop.org. And you can subscribe freely to the K-pop site for the YouTube K-pop site. Okay, we first consider the problem 1. Find the equation motion for the harmonic oscillator consisting of mass m and spring constant k. Newton's second law of motion is a force equals mass multiplied by the acceleration, the double time derivative of position vector. If you have a restoring force of a spring measured from the equilibrium point, here the spring is released to apply no force at all to particle. So this one is x equals 0, as in fact it is a vector, and if it is moving along a straight line, then we can use the Cartesian x-axis to pull out the Cartesian component, and we can describe the system in terms of one-dimensional variable only. The restoring force is minus opposite to the displacement from the equilibrium position, and it is proportional to the strength of the spring that is parameterized by the spring constant k. If you insert this into Newton's second law of motion, and the equation of motion becomes the second order linear differential equation. Remember that differential equation was created by the physics, but so to solve physics problem, people developed a theory of differential equation, just like the calculus was developed by Newton to construct the shell theorem of the gravitational force. Okay, if we restrict ourselves to one dimension, then we can pull out the unit basis vector of the Cartesian coordinate, and the equation of motion reduces to the simple problem. What is Newton's law of universal gravity? This is the universal force applied to any particle of mass. So for example, the mass of the sun and the mass of the earth applies to the attractive gravitational force denoted by the negative sign between the two massive objects. It is proportional to the distance squared inverse. The inverse square law means the strength of the force is proportional to the reciprocal of the square of the distance between the two particles. The strength of the force is determined by the universal constant that is a constant of universal gravity. And here, the direction is determined by the parallel to the displacement from one massive object to the other. And we denote x by the position vector of a particle we are interested in, for example, Earth, and Sun. We have mass capital M, and origin here, and this is why we find the displacement from the Sun to the Earth is x minus y. ER is the unit vector along this vector, so the gravitational force applied to this particle of small m is opposite to x minus y. So therefore, we have negative sign in front of ER hat. ER hat is the unit vector along the x minus y. Okay. The first is attractive action at a distance. There's no mediator between them. No connection is necessary. No contact is necessary. Inverse square law that respects one of our squares, where r is the distance between the two objects. Central force is that either parallel or anti-parallel to the displacement between the two particles that are interacting with each other. So it is also central force. Employing Newton's third law to find the center mass at the rest frame, center mass is at rest in the same frame. It is straightforward because the origin is chosen to be the center of mass. Then origin doesn't move at all in a frame of reference. Let's see. Newton's third law states that the force applied to the Earth, we have x is the Earth and y is the Sun. Okay, x minus y is the displacement from the Sun to the Earth, and force applied to the mass m, that is Earth, placed at x, is the net force and is mass multiplied by the acceleration of this particle. The other particle interacting with this gravitational force is mass capital M. We say it is a sun. The two forces are opposite and the magnitude is the same. Therefore, the gravitational force applied to the sun is minus F, while the force applied to the Earth is plus F. It's trivial to find a sum that is exactly zero. As a result, mass times acceleration, their sum must vanish. Okay, double derivative is zero. Double derivative of this is zero. Okay, as long as the mass is independent of time, and that is true in Newtonian mechanics. We recall that the center of mass of two particles is the average of the position weighted by their own masses. Because of this, I can take the derivative to find the velocity and acceleration of the center of mass. By the way, we have chosen the frame of reference at which the center of mass is placed at the origin. As a result, the coordinate, this one is a zero vector in the center of mass frame. As a result, if I take the time derivative for the first time and this double time derivative, either way, everything is a zero vector. We define the relative coordinate vector, that is the displacement vector from the sun to the earth. Oh, by the way, if you find the exact value for x and y in terms of the relative coordinates and the center of mass, because we are working in a CM frame, the center of mass information has disappeared because it is at the origin. From the center of mass, the distance of particle of mass m, cm, that is a 0, the origin, and particle of mass m. Okay, this distance is upside down, m to Kepler. We can see from the cm, these two directions are opposite. So this one has a positive sign and this one has negative sign. And this m, this small m, okay, this distance appears here and this factor appears here. Okay, so this fractional multiplication fraction is multiplied to the relative coordinate vector's magnitude, so that is the distance between the two objects. Okay, show that the total orbital angular momentum of the Sun-planet two-body system is conserved. We remember the force is 0. Then if the net force is 0, then the acceleration is 0. Just like that, we can construct the rotational version of Newton's second law. That is actually the torque is the time derivative of the orbital angular momentum. The linear version is the force is the time derivative of linear momentum, where the linear momentum is a mass times a velocity. Here, orbital angular momentum is position vector cross product force. And here, both of them are net. The algebraic sum of all of the torques, all of the forces applied to a single object or system of particles. All right, so we'd like to compute the net torque, x cross f, and this is the Earth, and this is the position vector of the Sun. And what is the force? This should be plus and minus f. So they are the same. It is not wrong, but I could have written this form to help you understanding. I mean, because this force is applied to the Earth and this force is applied to the Sun, and they are equal in magnitude and opposite. Anyway, the position vector, and what is the force? Force is the mass times time derivative. This is a linear momentum of the particle. The time derivative is placed outside. Okay, x cross p, linear momentum of the Earth. What is the linear momentum of the Sun? This position vector cross product, linear momentum. So mass of the Sun and velocity of the Sun. All right, so this total derivative is the sum of the torque. This is a rotational version of the Newton's second law. All right, here I repeat the definition of the total orbital angular momentum. And that is the sum of the orbital angular momenta of all of the particles. Here we have two-body system. Why don't we make use of the result we just have obtained? I substitute these values in here. I finally found a very simple formula. That is this. What's that? This is mu is called reduced mass. Reduced mass is the product divided by the sum. So you could have learned the harmonic average in mathematics class, something like that. Okay, this one originates from this physical problem. For example, the reduced mass of the two-body system. And in here, r is the distance between the two particles. We have defined the relative coordinate vector r, and that magnitude is r. Alright, so reduced mass multiplied by the distance between the two celestial objects multiplied by the angular velocity. Okay, so we recall that in the two-dimensional polar coordinate system, a vector on the two-dimensional vector can be expressed as a radius multiplied by the unit radial vector. The derivative of this can be computed by applying the Leibniz rule, the derivative of the first and the derivative of the other. And this guy's derivative is nothing but the tangential velocity. All right, we remember the cross product between the ER and ER parallel vanishes. ER cross E theta, so unit radial vector and unit tangential vector, that is identical to the E1 cross E2, and we know very well about that. That is a E3. We recall that the reason is that ER and E theta, they are perpendicular to each other. As a result, conservation of area velocity is called in the limit when the sun's mass is much greater than this, that the mass of the earth, then it can be approximately the same as small m, the mass of the earth, because this one is much greater than this, so we can make it approximately, and this is m. In general, it is not true, but it's in that case, the sun can be placed at the origin, that is the center of mass, and Earth swipes, and this is the orbit, and this is the angle measured from the sun. That the actual angle in the genuine problem is the center of mass, and this is the angle, and this is not the radius, but this is capital M, small m. This is the radius. So it is it's not a simple problem as this. However, let us simplify it in the limit as capital M approaches this point. All right, so the orbital angular momentum has been computed as mu r squared theta dot, and that is conserved. Why? The torque is 0. Sorry. As a result, we have area of this is orbit. It's not a circle in general, but in case if it is a circle, we can say it is a sector. So what is the area of this sector when the distance from the origin is r? I told you that this is not true. In general, the r is the distance between the two, not from the center of mass. But this figure shows the case when this guy is almost the same as the center of mass. All right, what is the area when this angle is d theta? We know this arc is r d theta. And if d theta is very tiny, then this can be approximated as a triangle, and it is perpendicular. So 1/2 r d theta. So 1/2 r squared d theta is the area of this sector. And this one can be expressed as a theta dot dt. All right. And then we are familiar with this. R squared theta dot is here. That is angular momentum divided by the reduced mass. So orbital angular momentum divided by 2, reduced to 2 times of reduced mass times dt. We divide both sides by dt to find out the velocity of area. So aerial velocity, the time rate of changing the swiping area by a planet on the orbit measured from the sun. That is the area velocity, and that is the orbital angular momentum divided by 2 times of reduced mass. Both of them are constant. So aerial velocity is conserved because of what? Orbital angular momentum is conserved. Because why? Because the force is central. Force is central. Force is parallel to this displacement, so they disappear. So it's zero. What is zero? Orbital angular momentum change is zero. That's orbital angular momentum is a constant vector. Okay, so we have verified Kepler's second law, stating that the area velocity of planet is constant. Now we'd like to study Kepler's first law, that is law of elliptic orbit. We remember F equals ma. This is acceleration, and we know it can be expressed in terms of the two-dimensional vector. And why don't we express in terms of a polar coordinate system? We have a radius, er hat. That is the unit radial vector. That is unit vector along the displacement from the sun to the earth. We take the second order derivative. Okay, another way is we have the formula for the force applied to the two celestial bodies. Okay, so ER hat appears here, and you need to take the double time derivative. Multiply this reciprocal of this to simplify the equation of motion like that. Now we are ready to compute this second derivative. We apply the Leibniz rule to find this, and we remember E theta and its derivative is opposite to the unit radial vector. And again, we can take the time derivative by making use of what? Chain rule. Chain rule, angular derivative, and then take the time derivative of angle. In a similar manner, I can compute the second order derivative and using all of these formulas. And then we substitute the values for these three. Finally, the second order derivative reduces to a simple, relatively simple form. This one has the two components, radial and tangential component, and we have radial component only. So, radial part can be combined together the radial equation, and this is the angular equation. We recall that the total angular momentum of this two-body system is completely conserved. It doesn't change at all. As a result, it's good to replace a theta dot in terms of orbital angular momentum L and the radius R, the relative coordinate magnitude of the relative coordinate vector. Okay, so this guy will disappear, and this guy will be simplified. Nothing but the conservation of orbital angular momentum, and this is reduced into this form. All right. Actually, we can convert this one as the energy equation, but we will learn later if possible. By the way, we'd like to simplify this, and we will, at the end of the day, we will find that this is identical to the equation of motion for a simple harmonic oscillator. Okay, let's see. Let's see. What's that? This is orbital angular momentum conservation, from which we can find the relationship between the time development and the angular change, the change in angle in orbit. Therefore, we can make a change of variable from time to angle, and details are given in here. And then what we want to do is replace 1 over r with simple variable u. And tedious calculation will lead to a very simple formula. Very simple formula. You have this, and you find it is a completely constant. So the solution of this differential equation is nothing but this constant. If this constant derivative is 0, so this constant plus something, you know, this, it is trivial. What's that? The solution of this is either cosine or sine. With some phase, that's fine, but we can always observe the phase into the angle theta from which we measure, and then we can multiply any number. Okay, so that number, we use the disnormalization, then 1 plus some cosine. All right. Finally, that kind of solution is expressed in terms of this. Why? This alpha over r, this originates from, this is u is 1 over r. Okay? Alpha, this guy is alpha. And epsilon, later we will say this is a semi-latus rectum, and this is eccentricity. And all of these formulas are represented by one of these forms. What is that? This is a circle. Circle is a cross-sectional. This is a cross-sectional area, and a boundary of this is the orbit. Circular orbit can be obtained by slicing a cone parallel to the base. If you make some angle relative to the base, then you will find an ellipse. And if you increase the angle to make them parallel to this slope, then you will find a parabola. And then you can make a steeper one, that is just like the just vertical direction. Then you will find an orbit that is a hyperbola. So all of these are called conic sections. The cross sections of a cone. Possible cross sections of cone. All right. So all of these are allowed by the Newton's law of motion and Newton's universal gravitational force. All right. Unfortunately, the Kepler knew only observable case, and it is the extreme case, and these two were not observed by Kepler. By the way, from this equation we can construct the effective potential, so whose negative gradient will give the effective force applying to the radial equation. This. So finally, the minimally allowed energy level, that is the total mechanical energy, that is the sum of the potential energy and the kinetic energy. Especially in here, kinetic energy is assumed to be the radial part, 1/2 mu r dot square. So in here, radial kinetic energy vanishes. So r dot is always a zero. R is a constant. That is a circle. If you increase the energy of the planet, you will find minimum and maximum. And this minimum and maximum shows that this R max from a focus or minimum from a focus. Okay, so this. And then if you increase further to let it critically free, that is closely related to the escape velocity 11 kilometer per. So this escape velocity at this, so it is in the limit as r goes to infinity, it is almost a stop. That is parabolic orbit. So if you launch a rocket to escape from the Earth's gravitational force, the minimum energy is available, should be available by parabolic orbit. And then if you launch a Voyager rocket, then you need to escape from the Earth and our solar system. So you need a lot of energy, much greater than that. In that case, it reaches the hyperbolic orbit. Okay, so although Kepler observed the elliptic orbit and he didn't know why, but physics of Newton's law of motion and Newton's gravitational force, that the universal gravity, that states that gravity is a central force, satisfied inverse scale law. That is the real beginning of physics. That's it for today. Thank you.